Organic chemistry, the new unit that we're going to start today, is based around carbon. We've talked a little bit about carbon just in our inorganic chemistry. It was not the star of the chapter. But anything that you classify as an organic molecule must contain carbon. Other atoms and elements you're going to deal with this chapter as well, carbon and hydrogen, that sometimes is often defined. It's really not just about carbon. Sometimes it is carbon and hydrogen is a guarantee in all organic molecules. So to really go back and review, it shouldn't be that hard since we just ended the chapter. We have the element or atom of carbon. The atomic number, that is 6. The atomic mass, roughly 12. Because it has an atomic number of 6, that means the proton number is 6. The mass of 12 on the periodic table, then because 6 and 6 will then give us our 12. And in a stable initial atom, we have 6 electrons. So therefore, the electron configuration, we didn't get into the S and P orbitals, so it would really just be a 2 in the first energy level, remaining 4. So there are 4 valence electrons in a carbon, which makes it pretty important. So if you were to draw the Lewis dot structure, it should look something like this. They are all unpaired. So that means in order for this to covalently bond, as it often does, it needs to find 4 more electrons. That can happen in 4 single bonds. That can happen in some double bonds. That can happen in some triple bonds. So what we will do today is we're going to learn how to build some carbon-based molecules. To start simple, we start with something called a hydrocarbon, and hopefully you can recognize why. If the term is hydrocarbon, then what this means, it is a molecule that contains hydrogen and carbon. A carbon skeleton is something you have to identify. If you were going to name and understand these simple hydrocarbons, the carbon skeleton is the first skill that you must achieve. So a carbon skeleton, we zoom out so we have a little bit more room. Carbon skeleton is the longest chain of connected carbons in the hydrocarbon. You'll see what I mean when we start drawing these. The longest chain means that they are side by side. A carbon connects to another carbon, connects to another carbon. They eventually start to do what is called branching, and that could be something you'll eventually then find out with this definition why it means the longest chain, because they get a little chaotic when you see them on a piece of paper. So I'll teach you how to locate the longest chain. An isomer, you see that prefix iso? We just ended a chapter where we talked about isotope. It's going to have a very similar definition. An isomer are 2 molecules that have the same formula but differ in position. So for example, C6H12O6, that is an organic molecule that you'll become very familiar with. Most often when you see that written, they will refer to it immediately as C6H12O6. They'll call that glucose, but technically that's the most common reference. But fructose, another sugar that we're going to talk about in this chapter, is an identical formula, C6H12O6. So by formula alone, you wouldn't be able to tell me which version of the sugar it is. It's how the atoms arrange themselves that is different. So an isomer, you can't tell which one it is. If there is a known formula, you have to know the position of some things. So an isomer, very similar to isotope, where an isotope was 2 atoms of the same element. These are 2 molecules with the same formula, but differ in position. So there is a similarity to the actual definition. Prefixes. To name some simple hydrocarbons, there is a list of the first 10. That's all we're going to deal with in this intro class. So these become familiar. You get to know them as quickly as possible. If the hydrocarbon has 1 carbon in its carbon skeleton, that prefix is meth. Eth is 2. Prop is 3. Bute is 4. We transition over to some geometrics with pent, hex, hept, oct, non, and dec. So those are prefixes. A prefix tells you how many carbons are in it. That's something that the quicker you understand the little methods to naming, the easier this becomes. So prefixes tell you about numbers of carbons. That's all they tell you. Now we're going to add some suffixes. Suffixes are dictated by the types of bonds that connect the carbons in the carbon skeleton. So on the next page, you have the first of three categories that we are going to talk about. Alkanes are hydrocarbons connected by all single bonds. So for example, let's draw something that looks like this. You see how what I have is 5 carbons. I first start with, I'm building the carbon skeleton. They all have a single bond. But that doesn't satisfy the needs of carbon. Remember, if I really go into detail with the Lewis dot structure, there are 4 valence electrons. There are 4 around this one. On this N carbon, one line signifies now they have the original electron and they're sharing with the adjacent carbon. So now there are 5. This carbon in the middle, it is sharing from the left and from the right. So technically, the way it's been drawn, this carbon has 2 unpaired, doesn't mean it's satisfied. This one has 3. So it continues down the line. To fill the void for all of these unpaired electrons, we're going to fill them with hydrogens. That's what makes them a hydrocarbon. So draw your hydrogens. So there you have a simple hydrocarbon. Building the name of this, you start with how many carbons are in the skeleton. We're keeping this very simple for right now. They're all included. So that means pent. Pent means 5 carbons. So that's why I translated 5 to pent. The ending, because they are all connected via single bonds, we are going to end this with the name ANE. So collectively, it is pentane. I know I drew a little separation just to kind of show you it's a prefix with a suffix. But it doesn't have to be written like that. You would write it as pentane. So you could, for example, if I had you draw octane, that would be something where there are 8 carbons connected, all single bonds, and what you do is you go in and you draw. Notice how many bonds a carbon can have. There's 4 every single time. This carbon has 1 single bond to a carbon and 3 to hydrogens because there are the availability of those unpaired electrons. An inside carbon has to only have 2 available bonds at the end of this. So you connect them with hydrogens. If we look at the total formula for pentane, the prefix tells me already how many carbons I have. If I go around then and count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the formula for pentane is C5H12. If you do more of these, what you'll start to realize is there's a generic formula where the subscript or number of carbons that are in the carbon chain, what you will do to figure out the hydrogens, double the number of carbons and add 2. So for example, 5 times 2 plus 2 is 12. Sorry, so there is the formula. Slide that over so you can see the C5H12. Alkanes are going to be your easiest ones to identify. Alkenes, we're going to see a little trend in this. These are going to be hydrocarbons, but they are connected with 1 double bond. We're not going to get too detailed. Don't ask me how to name all the other ones. I know you get very curious about all these exceptions. Let's learn how to do the basics one. Connected with 1 double bond. So for example, if I draw something very similar, what I'm going to do, here's an example. Let me draw the double bond between these 2 carbons. So that means this carbon right here already has 3 bonds, so it only has the availability to have 1 more connection to a hydrogen. Don't get hydrogen happy. You only have 1 right there. This one as well. 1, 2, 3. There are already 3 lines. So hydrogen, you start looking at how many connections they can have. That's why it's always easier to build your carbon skeleton first and fill in your hydrogens later. So what this is, we would say, once again, pent, because it has 5 carbons, but the ending corresponds to the ending on the actual name of the group. So this is pentene. Now the trouble here is, if I do this very quickly, underneath, if I drew the double bond in a different location, this is where the idea of, you gotta get tricky here. This one only has 2. This one would have 1. Sometimes I go too fast and don't recall. Right. There we go. So these are 2 different molecules. They would both start with pentene. So we have to identify a way to set, they are different molecules. The double bond is in a different location. They're not the same. They're isomers of one another. So what we do is we start numbering. 1, 2, 3, 4, 5. So this is the second carbon. So what I will do is I'll put a number followed by a dash, and it says pentene. So 2-pentene. Can you guess what this one would be called because of its location of the double bond? If you were thinking 1, you are correct. There is a little trick to this. Unfortunately, you can't always be looking left to right. So that what you do is you number in both directions. I know that your eyes always tend to go left to right, and I did that as well. 1, 2, 3, 4, 5. But to double check, you've got to count in reverse. Pretend this is now the end carbon and go 1, 2, 3, 4, 5. You're always going to where the starting of the double bond begins. So if I did 1, 2, I've got the number 2 that I could do. If I reverse it, it's 1, 2, 3. The rule is you always go in the direction that gives you the lower number. We're going to practice this more. I'm probably not going to get to that in this very quick video. I want to give you some basics. We'll go into a little bit more in class. So here, 1, 2, 3, 4, 5, it's the first carbon. That's why I did that. If I did it in reverse, 1, 2, 3, it wouldn't be till the 4th carbon that you hit the double bond, so I wouldn't choose that direction. You can think of it, if you want to draw one, it would be kind of if I reversed it. Now all the letters are backwards, but at least counting-wise, this is 1, 2, 3. So if you kind of see that, these are the same molecules. So on this one, I would count from the right. 1, 2, and it would still be the same name. I know that can be a little overwhelming. Eventually, it should kind of connect very, very simple for you. And the final one is the alkynes. So what you're starting to see here is the connections change by 1. So these are connected with 1 triple bond. So with that, keeping it the same way with the numbers, so I'm going to draw my carbon skeleton with 5. Let's pretend that we do this as the location of my triple bond. Now that I have the triple bond down, I'm going to go in and fill in, don't see, 3 and 1. So this carbon doesn't have any room for hydrogen, so I'm not going to draw any. Same thing for this one. This one has room for 3. So now I go in and fill in those hydrogens. What do you think we should name this? We should start with the number of carbons. That would be pent. What do you think the ending is going to be? Pentyne is how you would pronounce this. Now the number. If I go from left to right, it is 1, 2, 3. But if I go in reverse and start with this end of the carbon, it's 1, 2. So I'm going to choose 2. Maybe that made a little more sense now with the numbering. So that would be 2-pentyne. The final things that I'll go back and talk about is the formulas. So I did the alkane, which was C5H12, or the generic formula of the following. When you have any pentene, regardless of the location, you still start with the number in the carbon skeleton. So in both it would be C5. If I count the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, can you guess how to figure out the generic formula? It's the number of carbons and just simply double the hydrogens to 2n. Right, so that's where you get C5H10. Down here, it's C5, and then this is going to be 8. So you do a CnH2n minus 2, and that will be the formula all the time. From a formula, you can't identify the location. That's the hard part. The formula doesn't give you as much information. So I couldn't say, here's the formula, now draw an alkyne. Specifically with it between the second and third carbon, it's not possible. So formulas have a little limitation. I will draw these and ask you to name them or reverse it I will give you the name and ask you to draw it. So we'll talk about this a little bit more.